Okay, let's continue with the second lecture of today. So Vivian Poulin from Montpellier.
Yes.
He has prepared a couple of Blackboard talks on neutrino cosmology. And I think we will aim for 12:15 then for our break. No?
Great.
Okay.
Thank you.
Take it away.
Thank you, Marcus. Thank you, Mauricio, for organizing this school. And thank you to all the students. So many of you, it's amazing to be here. And I do sound a little sick. Promise it's not because I just arrived to Copenhagen. I was sick before from the heat wave and AC combination. Very stupid. And I'm sorry, especially to the people on Zoom, if I keep sneezing or having to blow my nose and it's annoying through the microphone. Great. So if I describe myself a second as well, I am a cosmologist. I would say I study mostly exotic properties of dark matter, dark energy, and neutrinos, starting from temperatures of keV and below. So very different from what we had before. So BBN era, it means in cosmology's talk, and down to the large-scale structure of the universe, and of course including the cosmic microwave background. So first, before I start, I just listed a couple of references that you find useful. The first one is really about neutrino cosmology, and in particular, the effect of massive neutrino, which I will get to. That will be the main topic of the lecture. This is actually completely free on AstroPH, on the archive. And there's also a book for which you might find pirate copies, but you should buy it, that has much more details, in particular also on the particle physics side, that came a few years back now. But with already the notes from archive, it's a great start to learn everything you need to know about massive neutrino. And then just about cosmology, because we will do some cosmology as well. I listed here the book by Daniel Baumann, who also has some lecture notes that are free, that are great to study cosmology. I studied cosmology through these notes, in fact. And since I wasn't sure of the scope of your research background, I just wanted to know who comes more from a cosmology background. Okay, great. So, no, but it's great because I know if I look at those guys and they're all like, yes, yes, then I know these are not the people I should follow, great, then it's perfect because the goal of this lecture is not to go too much into the nitty-gritty details of technical things. We will try to go through the main things that we learn about neutrino through cosmologies, which are really, first and foremost, the main goal is to measure the neutrino mass. That's what we are mostly paid for nowadays as neutrino cosmologists, is find a way to measure the neutrino mass. And why is that? Well, it's that because, so let's see. I'm going to try to work out this amazing blackboard and in ways that you can see, but let me know. So let's see. So the reason is because from neutrino oscillation experiments, we do not know the absolute mass scale of neutrinos. As we just heard before, what we measure are mass splitting between different states, neutrino states, where we have the larger mass splitting coming from atmospheric experiments and the smaller mass splitting coming from solar experiments. However, while we know from matter effects within the sun the sign of the mass splitting for the small mass splitting, we do not know it for the large mass. Oops, sorry, and I shouldn't do that. I'm already making a mistake. Sorry. It's 3-1 that we have learned. So let me put it on this side. Sorry. And so we know that delta, and so this means, because we don't know the signs, it means that we will be able to split neutrinos in two different ways. Either we have two heavy neutrinos, so we know the sign of this guy, but we don't know the sign. We only know the absolute value of that guy. So this means that we can have either neutrinos with a small mass splitting, so heavy neutrinos, two heavy neutrinos with a small mass splitting, and one light neutrinos. This is called the inverted ordering. or we have one heavy neutrinos and two small mass neutrinos. And this is called the normal ordering. And the numbers, if you want me to give you the numbers that you want to plug in for this small mass splitting, this delta M21 square, which is what I called here delta M squared sum. This is equal to 7.4 plus or minus 0.2, 10 to the minus 5, just to show you the orders of magnitude in this square. And this is defined as M2 square minus M1 square. And this we know the sign of. And then we know only the absolute value of the difference between the state 1 and 3. Which is what I've defined as the atmospheric neutrino mass splitting. Again, just to be very clear. And this one is 2.51 plus or minus 0.02, 10 to the minus 3 eV squared. Okay? What can cosmology do for us? Well, cosmology, as we will discuss, is sensitive to the sum of the individual neutrino masses. Where here I'm summing over the three different states that we have, the three different mass states. And if you work this out carefully, what you end up is that if you assume that the lightest neutrino, either using the inverted ordering or the normal ordering, you put the M1 to 0 in both cases, and you end up having a lower limit on what the sum of neutrino mass should be. And I'll let you do the little numerics, and you'll get roughly 0.06 eV if you are in the normal ordering, or 0.1 eV if you are in the inverted ordering. Okay? And so, to tell you where the lab is on trying to measure this quantity, the best bound that we have is from Catherine, which studied the beta decay of tritium and the endpoint of the beta decay of tritium. And the bound that they've got on the sum of neutrino mass is 1.35 eV. And that's science 20. It's really hot. Latest results of the Catherine experiment. And neutrino and cosmology, as I'll give you in a second, the numbers can actually probe bounds at this level, at the level of 0.06 eV. So this is really the main goal of, maybe I can give you the number now. The number, when you combine CMB from Planck, is the CMB, a satellite that has measured the cosmic microwave background, Planck CMB plus baryonic acoustic oscillation, and I will spend some time defining those things, don't worry. Baryonic acoustic oscillations, you get, so if you combine several experiments that have been measured the CMB, there is something else called ACT, Atacama Cosmology Telescope, and even a brand new one called South Pole Telescope, SPT, with results that appeared just a couple of weeks ago. So if you combine Planck, CMB, and BAO, the canonical result used to be at the level of 0.12 eV when you look at a paper from 2018, this is a 2018 bound. I forgot the archive number. I didn't write it down, unfortunately, but that's the baseline Planck cosmology paper that you find that has tens of thousands of citations. Recently, these have been increased thanks to a new BAO experiment called DAISY and this ACT that has increased to 0.0606 eV. So potentially excluding, and by the way, the limits I'm giving are to be understood at the 95% confidence level, 2 sigma bounds. So we are right at the level of the minimal mass in the normal ordering. So this is for when you add that. And when you add SPT just a week ago or 2 weeks ago, look at how crazy this has become, 0.048. What's happening? Where are the neutrinos? So this is what I want to sort of discuss today how this situation, not today, but through the topic of the lectures, how have we, reached this, and what does it mean, really? What does it mean in terms of cosmology? Should we just ignore cosmology? Or more interestingly, that maybe there is something deep about our universe, some new properties of the universe, and we will briefly mention the idea of dynamical dark energy. But of course, there is also the possibility that there are some systematic affecting the bound. So we'll go over where those numbers are coming from. Sorry, I didn't put this here, but really to understand, that's the main goal of my lectures, to understand how we derive those bounds. The second parameter that is important to us is the number of relativistic species, basically the number of neutrino-like species. So what you probably, so that's going to be the second goal of the lecture, depending on how far we manage to get. Not today, but over the three next hours. So we know from the boson invisible decays already at LEP that there are only 3 active neutrinos. So the number of active neutrinos coupled to the weak interaction is very tightly constrained. And this I give you the number I could find from the PDG, which are updated analyses with updated cross-section, blah, blah, blah. So very tightly constrained. But this is basically from LEP with an update, and you'll find the reference in the PDG, particle data group, if you're not familiar with the PDG. But so that's not what cosmology is going to be able to tell us. That's what cosmology is going to be able to measure. What cosmology is going to be able to measure are sterile neutrinos. Are there extra neutrinos that are gauge singlet of the standard model, not coupled to the weak interactions, but could contribute to N effective? So N effective, and I will define that properly later, don't worry, is the number of relativistic species, so things that have a very specific scaling with redshift as they dilute, relativistic species, the number of relativistic species other than photons. Everything can fit in here, other than photons. Because the photons, of course, these are the CMB photons. And the baseline number, when you do the computation in the standard model, assuming only a population of 3 active neutrinos, is 3 for the three flavor of neutrinos. That's how it's been defined. We've normalized it such that it's 3. And there's a small correction, which we will not go in the details of. But the small correction now, the latest value, because it changed, theorists like to tweak this number, you'll find 0.46, 0.45, 0.43 now. Is the latest I could find from a paper. Did I write it down? No, we'll give it later. I'll give it later. So you'll find 3.345 depending on how many loop correction and you have in your computation. And the complication comes from how the key thing you want to compute, will go through that, is electron-positron annihilation and how this talks to the neutrinos when that happens. But basically, these are just 3 for 3 flavors. And we will never be able to measure, at least not to the 3rd digit. I don't think we'll be able to measure %, but definitely not per mil with any realistic 10, even 2050 experiment. So it's just, I would say, a fun game to be played by theorists, because we can try to adjust this 3rd number, but we will not be able to test. Okay, and the current constraints on this, again, a fun thing is happening where, and when you combine Planck, ACT, and as I was saying, Planck, ACT, and DESI, I can't give you the SPT numbers. I couldn't find one that I liked, I will say, that corresponds to the combination with the data set that I wanted. So I'm going to give you one that's coming from just April instead of June, so still quite recent, 2.86 plus or minus 0.13. So a little under, the number of 3, but not that bad. Okay, not that bad. And this is what 68%, because this is a detection. We've measured that there were 3 relativistic species that are not photons in the universe, roughly 2.86 plus minus 0.13. So I give the numbers at 68%. And when I give upper limits, it's always going to be 95%. This is a convention in our field. Okay. So what I'm going to do for the rest of those lectures is to discuss first, the first lecture is really going to be about introducing the cosmic neutrino background. As we heard, it's everywhere. We are able to put constraints at the level of, 10 to the minus 2 on the absolute mass scale, 10 to the minus 1 on the level of how much there are. But as we heard earlier, it's an indirect detection that we've had. We've measured their gravitational properties, but not their electroweak properties through cosmology. Indirect detection. So this is why I guess there is wiggle room, because you're only sensitive to the gravitational properties which are degenerate with other things that may gravitate. That's why we are not necessarily, you didn't hear a Nature paper about the 0.048 EV. It was a quick note because most likely something's going on that we shouldn't do that last data combination. When we combine the CMB with the BAO to get that number, it was probably statistically ill to do that because we missed an ingredient in our cosmological model. But just to tell you that we're reaching that level, we should see the massive neutrinos, and we'll be able to test the presence. We are able to test the presence of gauge singlets, sterile neutrinos at the, what is this, percent, what is this, 10% level, something like that. And the second lecture is really going to be about massive neutrinos. I'm going to discuss the main two effects that we probe through cosmology. And lastly, we'll talk about N effective. That's the plan of the lecture. And N effective, I will try to put that in relation with something called the Hubble tension, just to understand, to tell you why. I won't go into many details, but just to tell you why there is a very, very, very hot thing currently in cosmology called the Hubble tension, which is a mismatch in measurement of the Hubble rate. And neutrinos may play a role, in particular through that parameter. Just wanted to discuss that briefly without going into all the details of that, but why people care about N effective when they talk about the Hubble tension. Okay? So let's start with the cosmic neutrino background. So before talking about the neutrino, let me talk about the cosmology part briefly. Just to tell you what we do in cosmology is to work to use general relativity. So we use G mu nu 8 pi G T mu nu, okay? And in this object here, there's a metric. Sorry, I haven't written down explicitly. Now I'm going to make a mistake on the board, but there's a metric here. So we need to know what metric to apply to the Einstein equation. And the metric is given by the so-called if F, so Friedman, Lemaitre, Robertson, Walker metric. How should I do that actually? Let me write it here. Friedman, Lemaitre, Robertson, and Walker metric, which is nothing other than the hypothesis of homogeneity and isotropy of homogeneity and isotropy of the universe on large. It's valid on large scales. We're talking of greater than hundreds of megaparsecs, reaching the tens of gigaparsec scales. So the FNRW metric can be very simply written as through the line element that takes this form dt squared minus the scale factor, which only depends on time because we are homogeneous and isotropic, times the spatial line element, this dx squared, where dx squared would take the form, for instance, dr squared plus r squared d omega squared. If we were talking about spherical polar coordinates, or dx squared, dy squared, dz squared, if you wanted a Cartesian coordinate. And this is for a flat universe, I should say. I'm going to work with a flat universe just to simplify a little bit the lecture and the notations. If there were if there were a curved space, you would add here some corrections. And it's also very useful in cosmology to introduce, you see that this has a conformal symmetry, so I can capture basically, I put that outside, and I make it explicit now. I have introduced something called the conformal time. Oops. And by the way, I'm using the mostly negative signature, which is not always what particle physicists prefer. So that's okay, right? Hopefully. So, and by introducing this conformal time, which is just a reparametrization of time, we can introduce just the first notion that's going to be important, the notion of distance, and in particular, the notion of comoving distance. So the comoving distance is simply requiring basically that you're following an object, or light, propagating along a null geodesics. And if you work this out, you see that what I'm going to get is simply tau. So I'm going to equate d tau and dx. Of course, there are c squares if I want it to work. I should maybe say it explicitly that there are going to be there are going to be factors of c that are going to disappear. And I'm going to pretend that it's on purpose, of course. And yeah, I mean, obviously now you see that what we get is simply the integral of the spatial line element. So this represents what we call the comoving. So from initial time, some emission to some reception, if I wanted to. This represents the comoving distance. If you put c explicitly for the sake of this exercise, represent what we call the comoving distance in cosmology. Okay, so this is although it's called conformal time, it's simpler to think of it as basically the comoving distance from some emission time to some, So if you were to take, say the Big Bang or something like this to today, you'd have, the comoving distance propagated by light. Okay, so this is, and the second thing that's important is now when we plug explicitly this metric inside of this equation, as you know, you take the 0, 0 component of that equation, but this is just going to give you a density. So typically, T mu nu, I should write it down. We are working with homogeneous isotropic universe and with perfect fluid. So it means that it has only diagonal terms, no I, J component, if you wish. So there is a rho, we write it like this, and pressure. And when we just take the 0, 0 components, we are going to, I let you do the derivation. You have to take, compute some Christoffel, the connections, blah, blah, blah. There is a fun exercise to do, but not on the blackboard here right now. But you know that you arrive at the famous Hubble law, Hubble rate, or the Friedmann equation, where we have introduced the Hubble parameter. So this is going to come from that part. And on the right, you're going to get is 8 pi j, which 8 pi j, by the way, is, we define that as some radius Planck mass. So we like to write that as the Planck mass. So it's like this. You'll see. There's no h bar, but up to h bar, and we have, just rho. So h square is rho over 3 m Planck square. So this is the famous Hubble rate that you can do tattoo of that. That tells us how the universe expands, okay? And why that matters is because here in this row are going to sit some neutrinos. You should understand that as the sum over all species energy density, which is going to depend on time. Okay? And the neutrinos are going to contribute to the expansion rate of the universe. Okay? Okay, so now let me move to the neutrino of the cosmic neutrino background. Maybe I can just write down in case I didn't write, in case it wasn't clear for everybody, but you can work out from the conservation of the strength energy tensor, the covariant conservation of the stress energy tensor. Sorry, I'm gonna mess it up. Yes. You can work out how the different species evolve over time, or with the scale factor. And you know that radiation species whose equation of states, which is the parameter that relate pressure and density, are going to be evolving like a to the -4 for radiation-like species. So this is normalized typically to the number today. So this is and matter is going to scale like a to the -3. Okay, where here I've normalized things such that the density here is the density today times the scale factor at some given. Okay, these are the typical things. And if you want a cosmological constant, well, you know very well that it's just a constant, literally. Okay, very well. And neutrinos are going to be very special, especially massive neutrino, because they're going to transition from scaling like a to the -4 to scaling like a to the -3. And this is going to leave a very specific impact on distance measurements and therefore on the universe, on our observables. Okay, so let's now move to the neutrino part of the. How should I do this? Because this one does not move, unfortunately.
Unfortunately, it does not switch.
Yes. So what I should do is try to keep stuff that are important over there. And okay.
You want to keep this, or maybe you can erase the top right part here. This part?
Yes. Yes.
Just continue.
Okay. So now we're going to set ourselves at early times, but below the temperature of the W and the Z boson. So we are at T below, let's say 10 MeV, sorry, 10 GeV for the sake of this exercise, because it's simpler. So here, what we want to know, the main question we want to know is what phase space distribution do neutrinos acquire, okay? And the leading process for that is electron-positron annihilation, okay? And collision. Oops, sorry, what am I writing? Okay? And in particular, this process here is going to be very important in setting the phase space distribution of neutrinos. And what matters here is we want to compare the rate of interaction of the neutrinos, which in the simple, we're going to take the non-relativistic limit. We're going to compare this to the Hubble rates. And, oh, sorry, yeah, well, you know, what we want to know is when is gamma much greater than h? Basically, when that is the case, then neutrinos are going to form a Fermi direct distribution. Okay, and if it drops below, then they're going to decouple from the bath, and they're going to evolve separately from all the other species. So we can just briefly write down that gamma. So we are at low temperature compared to the mass, so that's why we did this, so that we could simplify the shape of the weak interaction and cross-section. And basically, this process, if I'm a neutrino, is simply going to be given by the number density of electrons, so that's going to be proportional to the temperature cube. The weak interaction cross-section, which in this low energy limit is just Fermi constant times the temperature square, times the speed of light, because the relative velocities are speed of light here. And so this means that typically you have something that scales like T to the 5, okay? And when you compare that to H, which, as we said, is given by rho square over 3m Planck square, I'll let you do this as an exercise to see exactly, because on the board I'm going to mess up the factors and so on, but you'll see that basically what you find is that there is a transition right at 1 MeV. This is why the temperature of MeV is super important in neutrino cosmology physics and neutrino physics in general, is that above temperatures of 1 MeV, you have that, so at T greater than 1 MeV, gamma is much greater than the expansion rate of the universe. So you have many collisions with it before the universe has enough time to expand, if you wish. And when temperature drop below that, is the opposite, as you understand. And now it means that if I'm a neutrino and I look for an electron in the sea of particles, I don't have time. The expansion rate has made the expansion of has made the length scale grow, if you wish, and I can't find them. So I decouple. And from that, obviously, I form this distribution, equilibrium distribution. It's just the Fermi Dirac distribution. And what's important to realize here is that because all of that happens at very high energies, there is no explicit mass here. I only put the momentum of the neutrino. The mass of the neutrino, see, you're doing this, but I know that you're a cosmologist, so I shouldn't. So the mass of the neutrino is going to appear when I take moments of that distribution in order to compute the average energy, the number density, the energy density, the pressure, etc., etc. That's when the mass is going to appear. So the thing to understand is that from that point on, from below that redshift, from below that temperature, neutrinos are going to, unless there are non-standard interactions, something special, maybe they decay, who knows? The neutrinos are going to keep that distribution. It's a frozen, what we call a frozen distribution. They are not anymore, they're not anymore in thermal contact, they're not anymore at equilibrium per se, but they're going to keep in this frozen distribution. Okay? And by the way, this is assuming also that there is no chemical potential, no neutrino, anti-neutrino asymmetry. All of those are things that, of course, people look for. But the constraints on any level, for instance, of neutrino, anti-neutrino, so the constraints on the chemical potential, which is another way of talking about the neutrino, anti-neutrinos asymmetry, I believe, are at the level of 10 to the minus 2. I should be a little bit careful on whether it's really the neutrino, anti-neutrino asymmetry or the chemical potential. But bottom line is we know that there's deviations to these distributions are very tightly constrained from, I mean, at least from this, from asymmetries of neutrino, anti-neutrino. Okay. So this is why there is no chemical potential. Okay. So I should say that this is happening. There are corrections in reality to this coming from the fact that the decoupling is not necessarily instantaneous, and that what's happening at temperature of order 500 kilo electron volt is electron-positron annihilation, and that is going to give you annihilation. Okay, and this is the process that we will do a back-of-the-envelope calculation to understand how that affects the temperature of the neutrino, or rather the temperature of the photons. But this is the process that people try to compute carefully in order to correct the phase space distribution due to that process. So what's happening is because we are so close from the time of the decoupling that really, if you do things correctly, you realize that neutrinos actually still feel a little bit the effect of positron-electron annihilation on their phase space distribution, even though, strictly speaking, it happens after they've decoupled. So after decoupling, as I said, the neutrino keep their distribution unchanged. They are a hot Schroelich, and so what you find is that they're going to have their momentum that's going to scale is like A. Their temperature is going to scale like A. So really, the shape is completely unchanged. It cancels out from the ratio and from the distribution. But now what we want to know, so first is we can compute, once we have the temperature of the neutrino, once we have the phase space distribution from statistical mechanics, you know that we can derive everything we need to know, in particular, our cosmic neutrino background properties, such as its number density, its energy density, and its pressure. So the number, just to recall, sorry if it's going to be a break for boring for a sec, but just to write it down, that the number density is going to be given by number of internal degree of freedom of a particle over 2 pi square. I'm integrating over, sorry, let me write down explicitly first. So this is the phase space volume element. Then you have an integral over the momentum time the distribution of some species I, which, by the way, is valid to any species, okay? It's not just for neutrinos. And because we have a homogeneous and isotropic universe, we can rewrite this as 2 pi square dp. There's going to be a p square coming out of this. There are factors of 4 pi that canceled out here. And we have, again, our phase space distribution. Okay? And if you want to compute the number density, you have to perform that integral. If you want to compute the energy density, you do the same, but you just have to plug in an extra moment of the distribution. So you have the same p square 1, and here you have the E. This E is where the mass is hidden. This is p square plus m square, okay? And if you want to compute the pressure, same thing, which is important if you want to compute the equation of state and how they dilute. Sorry. You just do the same, but with the right prefactors, which are E squared over 3 times the distribution. And you see this over 3 comes here because of the, you know, the definition of T mu nu had like p's, you know, but 3 times. You have to cancel that out. Okay. Sorry. Okay, so now you can compute this, and you probably know already that they are simple. So these are in general complicated integrals, but there are solutions of that you can do analytically in the limits. Here I haven't specified yet what is the temperature, but I can just, if I can make, I'm going to take limit based on whether T is much greater than the mass, which is going to appear here, I recall, or the opposite. And the limits that you get when you do that, so in the limit where the temperature is much greater than the mass, that's the ultra-relativistic limit, or the relativistic limit. You have the famous relations that the number density is equal to number of internal degrees of freedom, the Riemann function divided by pi square times t cubed, and then it's either a 1 if you're a boson or 3/4 if you're a fermion. Okay? And rho, which is the other thing that's very important, is going to be pi square over 30 g and t to the 4. That's how you derive the thing that I've said before, that number density scales like t cubed, energy density scales like t4, basically because there's an extra factor of energy here. And this gives you, and there is the same little correction based on whether you're a fermion or a boson. And for the pressure, you would derive that it's equal to 1/3 of rho. Hence the equation of states. And yeah, I haven't written explicitly the generic equation that you do from this. When you take the 0, 0 component of that equation, sorry, the 0 component of that equation, so the sum, but you take the 0 component of that equation, you would have found that it looks like this. It's rho 0 today times a to the factor -1 times 3 times 1 plus w. That's the generic form of that equation. And so depending on the value of w, you would derive this equation. So this is for the relativistic limits. And for the non-relativistic limit, the opposite, you derive n is equal to g m temperature to pi to the 3/2 times the Boltzmann factor, the suppression due to the mass. Okay? So we are at equilibrium. You would, if neutrinos were extremely massive, they'd get depleted, you know, or dark matter, etc. That is, for instance, very important in setting the abundance of dark matter. And in the freeze-out mechanism requires you to stop this suppression at the right abundance. So this is a very important prefactor for massive particles. The density is simply mass times number density. There's some correction from temperature, but I'm going to ignore that. And the pressure is 0. Same thing. There will be some temperature here, but we are in the limit that it's very small, so we ignore. Okay?
So this E square pressure is correct, or just
what did I mess up? Tell me. Sorry.
So this E square in the pressure, this
Yes.
So is it E square or?
I think it's E square. Pretty sure it's E square over 3 in the pressure. But from what I wrote down in my notes, it was E square over 3, but we could check.
But the expression you have written P is equal to 1/3 of rho. And then if you match this, compare with two cases here, then that is our dimension.
Yes, I understand what you mean. I understand what you mean. Did I just mess up? Yeah, it's possible that I messed up. It's true that here from dimensional, just for dimension, it doesn't look correct, so I should be careful, but I forgot. I'm pretty sure that the pressure is defined like this, though, so we can check that from a textbook later, but that's a good observation. Okay, I'm going to put a question mark here because I've got a little doubt. But we'll think. I'll come back to that. Let me check again afterwards. Okay. Oops. Okay, and so now the big question is, what do we have to plug in for neutrinos? Is the big question. What is the T that we have to plug in for neutrinos? And so what we are going to do is to use the conservation of, so what is the temperature of the neutrinos that we have to plug in to compute the properties of the cosmic neutrino background? So in principle, at high temperature, at high energies, before decoupling, T nu is simply equal to the temperature of the bath, which we take to be, which is the same as the temperature of the photon or the temperature of the electrons. They're all equal because we are in thermal equilibrium. But after decoupling, so this is for gamma greater than H or T greater than NB. But after decoupling, this law is not going to stand because of that process, because of electron-positron annihilation. And to understand what's happening at positron-electron annihilation, what we are going to use is the conservation of entropy. So we're just going to use the law of thermodynamics. So let's use the conservation of entropy. So we're going to use the conservation of entropy to know how the temperature of the photon is changing as at the electron-positron annihilation. So we're just using basically, first law of second law of thermodynamics. Then we are going to introduce, so basically you start from this, you use the fact that the universe is homogeneous, so basically integral over volume are trivial, and we're going to introduce what's called the specific entropy, because instead of working with global quantities, we want to work with density, really. So if you wish, is the same thing as the entropy density, or entropy density, which is simply the entropy divided by, the specific entropy, often it's written small s, is the entropy of the system divided by the volume. Okay? So then we don't have to care too much about what's the volume of the universe in that context. And so if you do that and you simplify basically the V part because of the homogeneity, you end up with simply with the fact that S is equal to, yes, sorry, yes. You're gonna get, I forgot. Yeah, you're gonna get energy density plus pressure. feel like I forgot a number density times somewhere, but I'm messing up already. Okay, so you should get an energy density plus pressure, sorry, divided by temperature. Okay, so the important part is that you're going to get the specific entropy is given by the energy density plus the pressure divided by the temperature. Very good. So what we're going to do now is we're going to have to plug in our expressions that are here, in this expression here. And when you do that, first you realize that what's going to matter the most, because of these cube factors and these repressions, etc., when you count the entropy of the system, what's going to matter the most is what particles are relativistic as opposed to non-relativistic. Basically, when a particle becomes non-relativistic, their entropy is removed from the medium. The specific entropy is removed from the plasma and heat up the rest of the particles. That's what's going to happen. So if you count correctly, yes.
So when neutrinos become non-relativistic,
much later, because here we are talking for the moment of the very high energy, temperatures of order of MeV, mega electron volt.
So what's the specific ratio?
I'm going to tell you in a second. We're going to do it. Okay. But you can derive it simply from requiring that the mass is of order of the temperature. Okay? But we need to know what is this in order to define that non-relativistic transition. Okay? And so, yes. So if you plug in the expression, what you're going to find is that the total entropy, which is the sum of each individual specific entropy, which we're going to call S now without a little index, is going to become 2 pi squared over 45 times T cubed times the number of degree of freedom that's relativistic, this G function, which takes a form of so it's a time, so this is temperature dependent and it has threshold. Basically, when a particle becomes, the temperature becomes smaller than the mass of a particle, these things drops by the number of degree of freedom associated with that particle that becomes non-relativistic. So it's a sum over, so you have boson and fermions have slightly different prefactors. So you're going to have the number of internal degrees of freedom, the number of spin, whether particle and antiparticle, helicity states, so flavors, etc. So times, sorry. And here, the simplification is we're going to put a heavy side, where it's basically a heavy side of the temperature, minus the mass. Okay? So basically, when the temperature drops below the mass, it kills this sum. And you have the same thing for the fermion, sorry. You have the plus fermion, where, I'm sorry, now you can't see nothing, but it's the same, but you're going to have a 7-8 in front because of the energy density. Okay? You're going to have a 7-8 here that's going to appear. And what you can also derive from this equation and from this expression, sorry, just because of the fact that this scale is like t to the 4 and there is a divided by t, this means that this thing is proportional to a cubed, a to the minus 3, sorry. Okay? So this means that there is conservation of this product, which is simply the conservation of the co-moving entropy. There's a co-moving conservation here. When you see this type of things, it means there's a co-moving conservation. The total entropy is conserved, but the entropy density dilutes like the volume. That's all it means. So this is equal to 0. And so we are going to use that fact in order to derive, because of the change in specific. So this guy is conserved, except, of course, except at the moment where you have this mass thresholds are hit. When the mass thresholds are hit, then this guy suddenly drops. Okay, and this is what we're going to use. So this means that we can write. And by the way, I should have written it explicitly. I'm sorry, that because we are talking about, there's going to be relativistic species that are going to contribute mostly. You see that there's going to be a relation of the form 4/3 of rho over t. There's going to be something like this that's going to pop. Okay, plus the contribution from massive particles, but the massive particle drop out of the count because of the scaling with temperature. That's just make them much less relevant because of the Boltzmann suppression. The Boltzmann, these prefactors actually should represent this Boltzmann suppression. That's because all of these guys come with that Boltzmann suppression here. So this is what this heavy side is representing. Okay. Very good. So now this means that I've got something such that I've got that in this, so equal 0 implies that I'm going to have something of the form. So I'm going to have something of the form like that, gt to the 4. This is just coming from my density divided by t. So I'm going to have a g, this function. So I'm summing over all the species. So this is why I have this gs here, this g total that's going to appear, time t cube, okay, t to the 4 divided by t, time a cube. And that guy has to be constant, okay? And this is what we're going to use now, because it has to be constant, but there's going to be a drop at a specific time that's going to boost the temperature, basically. This guy is going to go down, but this guy has to stay constant. So this guy has to increase. So what you find is that the temperature, so here you've just derived what I said before. You just derived that unless the number of degree of relativistic degree of freedom changes, if it's fixed here, no more threshold of temperature and mass, the temperature scales like 1 over I. Just from specific entropy conservation. And when this happens, when the degree of freedom change, then you're going to hit the medium in order to keep, you're going to hit whatever is left in thermal equilibrium. And whatever is not in thermal equilibrium is not going to feel that temperature hit. Okay? So this is another equation that's very important. And now we're going to apply that to our neutrinos. Where what's going to happen is that the number of degree of freedom of the plasma at electron-positron annihilation, GS, drops. And what we have is that GS goes from, so we can count before we have, so we are after the neutrino decoupling. We are at temperatures of 511 keV here. So we have two degrees of freedom for the photons, plus fermions have plus now the number of degrees of freedom for these are the photons. Write it here. Spin, basically. And here we have the number of degrees of freedom for the electrons, which are positrons and electrons, so 2, and the spins, the 2. Okay, so 4. These are the electrons. And the 7/8 is the prefactors for fermions. And this means that this is 11, 2, and then this guy goes out, so now we have 2 post after the positron electron annihilation. Okay, so we go from 11.5 to 2 remaining degrees of freedom. Conservation of entropy means you have to increase the temperature of your photons. So the photons temperature goes from 11.5. So I plug it now. I just plug in the number of degrees of freedom here. 11.5 T cube A cube equal. We're going to do the instantaneous approximation. this is what would give you, that's what you want to correct. That's where the complication enters, I was saying. Here we are assuming instantaneous decoupling, sorry, annihilation, is equal to 2T prime after the post, the energy, the temperature after the annihilation, acute, okay? And this T here, the pre-annihilation, is the same as the neutrino because we were before the annihilation. And this prime is going to be, post-annihilation, is going to be the CMB photons today. So here I'm cheating a little bit, okay? I've cheated here, but this is our temperature of the neutrino before the annihilation. And after annihilation, in the end, is the temperature of the photons that we measure. You just work out the math and you get the famous formula that the temperature of the neutrino is equal to 411 to the 1/3, the 1/3 power we derive from the cube here, times T gamma. This is for neutrino cosmology, it's also a very, very important result. Okay? And from knowing now that we have, so this is what we expect from standard model neutrinos that have decoupled at the MeV. There are corrections, as I said, because electron-positron annihilation occurs very close to MeV. So there are some corrections, but the correction are this 0.043, which we will not measure. So basically 3 is the number. So this temperature is what you need to care about. And from that temperature now, we can define number density, energy density, and pressure for our neutrinos, and when they transition to non-relativistic. I want to keep this equation just now.
I have a question.
Yes, please.
So if you instantaneous, so how would one go about it?
Yes, so what's happening is if it's not instantaneous, because I cheated when I wrote down the cross section for the weak interaction. There are high energy neutrinos basically that can still contribute to the bath, that still are coupled to the bath, and because of that, they're going to feel the fact that the the electrons are reheating the photons, and then you solve here. So to really solve the fact that it's not instantaneous, you have to solve a Boltzmann equation. So you just have to compare the Hubble rate to the rates at positron-electron annihilation and the coupling, the neutrino electron scattering. You're going to have various terms. And if one is what I've assumed here is that the annihilation is much greater than h. Basically, is what this is just. I'm calling instantaneous just the fact that I took my Boltzmann equation and I said that the E plus E minus annihilation was much greater than h. So then I don't have to take into account the fact that A evolves a little bit over the time scale. Okay?
But is it not canceling out on both sides?
Well, to equalize here, I've already assumed, if you wish, the instantaneous thing. So you would, if you solve the Boltzmann equation correctly, you'd see that this comes out if in the condition where that's verified. And that's what we call the instantaneous. This is, yeah. Thank you for the question. Okay,
so questions? Questions? No?
Have I lost everybody, or is it no question because it's good? Or it's great? Great. Okay, well, if you haven't followed this derivation, all that matters at this point is that we know the temperature of the neutrinos, and we know it extremely well because we know the temperature of the photon of the CMB from Kobe Fires already back from the 1990s. And the number that you want to plug in. So this, did I do the numericals? Can someone do this numerical calculation? Isn't it 1 over that? That's 1.9. Yeah, the temperature is 1.9, but I just wanted these prefactors. But yes, the temperature, exactly. The temperature of the neutrinos is 1.9 Kelvin, and the temperature of the CMB photons is 2.7255 Kelvin. So really, in the standard model, we know them. We know their temperature, super high accuracy from this approximation. Okay, and so the prefactors is just this ratio. Okay.
Can I ask?
Yeah.
There's also a question on Zoom here from Vilas Amador. could the effective species of neutrinos be modified by beyond the standard model
Yeah,
of physics?
of course. Yes.
Yeah.
Yeah, I mean, you can, what's going to happen is if you have, if you couple, well, you could modify this quantity depending on whether there are additional degrees of freedom within the neutrino sector, whether it's, if it's a thermal neutrino, but yeah, fully thermalized, definitely not, but you could slightly change indeed these degrees of freedom from from beyond the standard model physics. So yeah, I just wanted to draw just for a second the temperature versus scale factor just to see what we have derived here is that temperature scales like A. So if I'm at 10 to the minus 10, 10 to the minus 8, here I am at MeV temperature. Here I have the 500 kilo electron volts, the mass of the electron here. What we've derived, so I'm going to mess it up, but it should just be I'm trying to go from here to here. It's just a simple linear law because T proportional to 1 over A. Okay, so this is what's happening for the neutrinos. And for the photons, what we're saying is that they're the same. And then at some point, electron-positron annihilation. They go a little larger. Oops. Should be parallel. They get a bump and then they're parallel again. But that ratio is constant and is this famous 411 to the 1/3. Okay, that's what we just derived. And we can now count the number of neutrinos that we're going to have. So the number density of relativistic neutrinos first is equal to, if we take our formula, we're going to have a 3/4 number of fermions. We are going to have, so we're going to normalize everything to the number of photons. So that's typical of in cosmology to normalize, as I said, everything to the number of photons, of CME photons. And in here, there is a 2. There's a 2 coming from the fact that we have 2 spin states. So a technical question is, should this number change if you're a direct neutrino or a Majorana neutrino? Given that the number of degrees of freedom might be different. You might think for a direct neutrino, there's a chiral counterpart, and the anti-neutrino is explicit, whose anti-neutrino is different from the neutrino than the Majorana neutrino. So the answer being no, because we have never observed right-handed neutrinos. They are not actually formed in the early universe. And so whether you're so you have to actually compute this. You have to do things at very high temperature to see whether you could produce the right-handed neutrino in the early universe. But the answer is no. And the number density of Majorana or direct neutrino is the same at the end. And so the way we normalize this is this. Then we will have a 411 here. That's going to come from the temperature Q. Okay. And then here is where we put our N effective parameter, because of course in the number of degree of freedom, there's the fact that there's 3 flavors of neutrinos here. Okay. So we have 2 helicity states basically, and the 3 flavor of neutrinos. Okay. And this, if you plug in the numbers, is 112 per centimeter cubes time N effective. About 300 neutrinos per centimeter cube, cosmologically speaking. This is what an experiment like Ptolemy, for instance, is going to try to detect. But we have not detected the number density of the neutrino. We've detected their energy density. And the energy density, again, famous expression, 7/8. And that's, of course, again, assuming mu, right now I'm at high temperatures, I'm assuming mu is equal to 0. 411. So now the T to the 4 gives me a 4/3 times the energy density of photons. Okay? And in cosmology, this is how we define really a typically an effective and any additional relativistic species decoupled from the standard model, but only gravitationally coupled to the standard model, would contribute to an effective. So if you are a dark matter model builder, maybe you like dark radiation, for instance, is something that's very common in dark matter models, that would contribute here, you know. But in the context of neutrinos, this is where the sterile neutrinos would also change that number or value. Okay? And so that's for the relativistic limit. But there is another thing that we like to define is in the non-relativistic limit now, when the neutrino mass is big in front of their temperature. So if I look at this part, well, the number density, I'm not going to write down, but starts to get, you know, a Boltzmann suppression. So if you see, depending on the mass, you're going to have Boltzmann suppression to the number density. And the energy density, which is simply, we can write down as, let me write it down explicitly, the sum, the rho, simply, so you're going to have a sum of, well, I'm going to put in all of the neutrinos, so we're going to have the sum of the mass okay? And we are going to times the number density, and this typically you can compute it explicitly. Sorry, let me go back one step before I write the formula. But this can be computed explicitly. It's a number in the end, basically coming from this formula, okay? And multiplying by the mass gives you their energy density, assuming that the mass is very small, you know, basically. And then what we like to do, sorry, is to normalize. I should have done it before, but we normalize energy densities to the total, which we call the critical in a flat universe, is the same energy density today. The critical is the sum over its, let me rewrite it. It's the energy density today. Here I'm using the flat universe approximation, so it's the same as the critical energy density and m Planck squared. Okay, so rho critical is just a normalization factor to today. Sorry. Yes, that's right. That's right. Okay, and this is what we call the omega parameter. The sum of the omegas equal 1 because we are in a flat universe and the total energy density is equal to the critical energy density flat universe. So omega nu, and this is where you're going to find this famous expression, and where you have the sum of neutrino mass divided by 94 electron volt. And to derive that number, you're going to have to compute what is the critical energy density today. So you have to know what is the value of the H0 parameter today, roughly. So, sorry, I should say there is times H square here, times H square. I forgot the little H because we don't know. So this is, you can rewrite as 3 m Planck. Well, small h is just equal to 100 times H0 norm in kilometer per second per megaparsec. Sorry. So the H square is just coming from the fact that we don't actually know the total energy density. It's a free parameter of the model. So here's an H square. And this prefactor is basically the Planck mass here. Well, divided, you know, and the prefactor that matters for the neutrinos. Okay. And so then we can ask some simple questions.
Maybe yes. Could this be a good time for our lunch break now?
Oops,
because
I'm already...
we have already 20 past 12.
Okay, I'm going to do one thing and then I'm done.
Okay.
One thing is to say, sorry, I didn't pay attention to time. It's just to ask, because it's fun, and then promise I stop. Given that we've derived the energy density of massive neutrinos to be, so we have said that omega nu H square is equal to I just wanted to show you that we can derive a simple bound on the neutrino mass that's actually interesting. imagine that we could ask, well, sorry, we can ask one thing. We can ask, sorry, what if this is, sorry, could neutrinos be dark matter? Is one, I'm going to stop here. Can neutrino be dark matter? And what you see from this equation, we can quickly derive that. We have measured that the energy density of dark matter is about 0.12 in these units for this product. So we can very quickly see that to be dark matter, neutrinos would need to have a mass that's about 11 eV, something like this. Okay? And that's completely ruled out nowadays by cosmology, but also by, so no, dark matter. Neutrinos are not dark matter. But this was one, was a very big question back in the days, whether neutrinos could be dark matter. Okay. And I'll summarize the lecture next time. Thank you very much.
Thank you. Okay, in the interest of time, thanks a lot. In the interest of time, I would say we go for a lunch break now, and then we are coming back at 1:30 with a lecture by one of our, by Pablo actually, right? Yeah. Okay, so lunch should be in auditorium C. We also have some sodas. Yeah, do you want to say?
No, everything's there.
Everything's there.
2 sets of sandwiches, one with coriander, one without coriander. It's mine. So,
Okay. Thank you.
Thank you. Did you mute me off?